Hello everyone and welcome to lecture. The topic of this lecture video will be what are called improper integrals and exactly how to evaluate improper integrals. So improper integrals are essentially integrals, so definite integrals, over infinitely sized domains. And we'll see that there are actually two types of improper integrals, type 1 and type 2. And we'll kind of investigate these in this lecture, how to evaluate them, and also how to apply them using some of the previous formulas that we've derived. So specifically in Calculus 2, we've developed this idea of the definite integral or the accumulation of a function. So the definite integral from a to b of some function f of x with respect to x is just we call this the definite integral of the function f of x over the interval from a to b. And we've seen through numerous examples that this is the same thing as the accumulation of the function. Or the net area of f of x on the interval from a to b. You'll remember that we have, for any continuous function, that this definite integral from a to b can be evaluated using the antiderivative of the function. We typically call this the capital letter of whatever the function is at the endpoints, or f of b minus capital F of a. Where capital F of x here is the antiderivative of the function that we're taking the definite integral of. So we've seen through a number of different methods in this course that there are many ways to compute the antiderivative. These include the substitution method, integration by parts, or IBP, partial fraction decomposition, PFD for short, and trig substitution, or trigonometric substitution. we've also seen a number of different ways of applying the concept of definite integral to calculate real-world quantities. So applications include arc length, surface area, volume, the center of mass, the total mass, and the center of mass of an object, moments of inertia, and we can also use this to get the probability of a certain scenario if f is a probability density function. We can use this to compute the work, energy, and even force and power produced by a certain force. And the applications really aren't limited to this list. The applications of the definite integral are, in some sense, endless. Really, any time you have a function that's integrable that you can integrate, you can go through and come up with some sort of application for the definite integral. So we say that a definite integral is an improper integral if the set of that we're integrating over has infinite size. And realistically, this can happen in one of two ways. The first way that it could happen is that the integrand, or the interval of integration, continues on forever. The interval being integrated continues on forever. And this would correspond to the bounds of the interval of integration, so a or b being negative infinity, positive infinity, or possibly a combination of both. And the second way this can happen is if the integrand f of x, the function being integrated, contains a singularity. This is specifically like an asymptote, where the value of the function, so where at some point f of x goes to plus or minus infinity. So the value of the function being integrated blows up. Turns out that there are actually many examples where this scenario is realistic, but the accumulation under the function ends up being finite values. Even though the function itself blows up and has a singularity or an asymptote, the integral of the function actually ends up converging. So we separate these two types of improper integrals into two types. We'll call type 1 the type where we're integrating over an infinite length domain. And the notation for this is the following. We see that the improper integral of a function over the interval from, say, any value c, any real number c, to positive infinity has the notation. We write it almost exactly how we would write it in the normal case, where the upper bound is a number, but we just say that the integral of f of x from c to infinity of some function f of x is the improper integral, or the accumulation of this function from some value c all the way out to positive infinity. This corresponds to, say, taking the integral of a function from some value right here, we'll say c of x, all the way out to positive infinity. So as far as you can go. The function maybe looks like this right here. It's decreasing as x gets larger and larger and larger. The improper integral from c to infinity is the accumulation under this function as x gets larger and larger and larger. So mathematically, we can define this as the following type. We define it in terms of a limit. We say that this is going to be the same thing as the limit as b goes to positive infinity of the normal integral from c to b of the function f of x dx. And what this allows us to do is just consider what the normal integral is from c up to some b value, some positive b value. That's what's shaded in green right here. So we consider what the normal improper integral is of a given function on some interval from c to b, and then we just take the limit of that result as b goes to infinity. So we say that if this limit exists, the limit as the upper bound goes to positive infinity, so if the limit exists, we say that the improper integral from c to infinity converges. And if this limit does not exist, or dne, then we say that the improper integral diverges. So we want to kind of have some sort of labeling here. So for type 1, this is the improper integral of type 1 of the first type. You can also consider an improper integral of the second type, or the integral of a function from, say, negative infinity up to some fixed c value. Which would again correspond to, say, if this is our y-axis and this is our x-axis, you could have that the function starts here at c, then maybe goes down. It looks like this, getting smaller and smaller and smaller as x gets smaller and smaller and smaller. So in both of these pictures, y is equal to some function f of x. And you could consider the improper integral of this function from negative infinity up to this c value, which is the net area, or the total positive area, minus the total negative area of this function as you get closer and closer and closer to negative infinity. So we say this is the improper integral of the function f of x from negative infinity to c, or all the way out as x goes to negative infinity up to including c. We define this in a very similar way. We say this is the same thing, or it's defined as the limit as a goes to negative infinity of the integral from a to c of f of x. So just like before, we say this is going to be the, going to first take the improper integral, or the normal integral, and it's not improper, from some fixed a value up to c. It's this green area, or this green net area right here. We figure out what that general improper integral is for any value of a, and then we just take the limit as a goes to infinity. And again, we say that if the limit exists, then the improper integral converges, and if the limit does not exist, then the improper integral diverges. So this is how we define the second type of our type 1 improper integral. The third scenario is to define what happens if you have an improper integral from negative infinity to positive infinity, where you want to define the improper integral function from negative infinity all the way up to positive infinity. This would be, let's say we have a full function defined for every value of x, and we'll say that it looks similar to a sort of combination of the first two types. Maybe f of x looks like this. The improper integral of this function we want to be the net area under this function, or the accumulation of this function from negative infinity to positive infinity. And this is one area where we want to be a little bit careful. It turns out that this is a very important note here. This is actually not the same thing as the limit as L goes to infinity of the integral from negative L to L. So this is not the correct definition of this improper integral, the improper integral from negative infinity to infinity. There are many examples of functions, really any odd function that you can think of, where this value is going to come out to be 0. So for odd functions, or functions that are that look like sine of x, where the f of x is equal to negative f of negative x. This is something that's satisfied by any, or negative times f of negative x. This is something that's satisfied by any odd function. The improper integral is not defined like this. This turns out that this limit is a special limit, and it's called the principal value, or PV, of a given function f. This is not the same thing as the improper integral, so don't be confused here. Sometimes this integral will exist, but the actual improper integral of a function from negative infinity to positive infinity will not exist. So you got to be very careful with this. For odd functions, the principal value will always be equal to 0, but there are many examples of odd functions with a principal value of 0, or for any odd function, the principal value will be 0, but there are many odd functions that don't have a convergent improper integral. Some functions will have a convergent improper integral, but in general the principal value will be a different value. So it's really important to make this note. So that the basis for defining what the improper integral is of a general function from negative infinity to positive infinity is the following. And it relies on the property of the integral. It's the additive property, the property of additivity. It says that for any interval from a to b, if you take any point in between a and b, the integral from a to b is the same thing as the integral from a to that point in between, we'll call it c, of f of x plus the integral from c to b of f of x dx. So we use this additivity property and we say that the improper integral from negative infinity to infinity of type, this is actually of type 3. So it's a type 1 improper integral, and it's the third subtype for the improper integral of type 1. I should change this right here to 3. So we use this additivity property to define exactly the improper integral from negative infinity to positive infinity, or the third subtype of these, the improper integral of type 1. So this third subtype is going to be defined by saying for any value of c, no matter what value of c you choose, the improper integral from negative infinity to f of x dx is going to exist and be equal to the improper integral from negative infinity to c of f of x dx plus the improper integral from c to positive infinity of f of x dx. So for any value of c you might choose, let's say we choose this value of c right here. The improper integral of the function from negative infinity to positive infinity will exist if the improper integral exists from c to positive infinity. So this improper integral exists, and if the improper integral from c, or negative infinity up to c. So this improper integral right here exists. So the improper integral of type 1 subtype 3 exists only if two other improper integrals exist for any value of c. This works for any value of c along the x-axis. So let's go through and do some example problems. We'll start with the function 1 over x. We'll just try and evaluate the improper integral of the function 1 over x from 1 to infinity. And this corresponds to the accumulation under the curve 1 over x from 1 to infinity. And 1 over x looks like this right here. So from our definition of the improper integral, this is the same thing as the limit as b goes to infinity of the definite integral from 1 to c, or 1 to b of 1 over x dx, which is the same thing as the limit as b goes to infinity of the antiderivative of 1 over x is the natural log of the absolute value of x from b to 1, which is the same thing as the limit as b goes to infinity of the natural log of b minus the natural log of 1. Natural log of 1 is 0. And so this is the limit as b goes to infinity of the natural log of b, which is positive infinity. So we say that the definite integral of the function 1 over x, or the improper integral of the function 1 over x, from 1 to infinity diverges, because this limit is equal to positive infinity, so the limit doesn't exist. If you look to, instead of the function 1 over x, you look at, say, the improper integral of the function 1 over x squared. We'll do an improper integral of type 2, or type 1 subtype 2. Do the integral from negative infinity to negative 1. Okay, this corresponds to the improper integral of the function 1 over x squared, which looks like this. From negative infinity up to this point 1 right here. This improper integral is going to be the limit as a goes to negative infinity of the integral from a to negative 1 of 1 over x squared dx. This is the same thing as the limit as a goes to negative infinity of the antiderivative of 1 over x squared is going to be negative 1 over x from negative 1 to a, which is the same thing as the limit as a goes to negative infinity of 1 over a we'll plug in directly. It'll be negative 1 over negative 1 minus negative 1 over a this is going to be the limit as a goes to negative infinity of 1 plus 1 over a, and 1 over a goes to 0 as a goes to negative infinity. This is going to be 1 plus 0, or 1. Which means that this improper integral, the improper integral of this function from negative infinity to negative 1, converges, and it exactly converges to positive 1. So you might see this example right here and ask exactly, for any power p, does the improper integral, or what values of p does the integral 1 over x to the p converge for, right? So like 1 over x squared converges, but 1 over x to the 1, or 1 over x, does not converge. So for what values of p does this integral converge? This is sometimes called a p improper integral. And sure enough, we can go through and directly figure that out. We already have that for p equals 1, it diverges. And this improper integral is the same thing as the limit as b goes to positive infinity of the integral from a to b of 1 over x to the p and this is the same thing. This is going to be equal to the limit as b goes to infinity of, when p is equal to 1, this improper integral is equal to negative, or it's equal to positive ln of the absolute value of x from b to a. This is when p equals 1. And when p is not equal to 1, this is just going to be equal to 1 over negative p plus 1 x to the negative p plus 1 from b to a. This is when p is not equal to 1. But when p is any number not equal to 1. So we've already seen that this limit right here as b goes to infinity of this expression when p is equal to 1 is positive infinity. So the integral diverges when p is equal to 1. And for this secondary limit right here, when p is not equal to 1, we have the limit as b goes to infinity of this expression right here, which is going to be the same thing as the limit of 1 over 1 minus p times b to the 1 minus p minus a to the 1 minus p. Or this is 1 over 1 minus p times the limit as b goes to infinity of b to the 1 minus p minus, and the limit as b goes to infinity of a to the 1 minus p is just a to the 1 minus p, because it doesn't depend on that b at all. And it turns out that this limit only exists if this exponent right here of b is negative. So 1 minus p is less than 0, or if p is greater than 1. Because if p is less than 1, or 1 minus p is less than, so if this is less than 1, you're going to get that this is going to be the same thing as the limit as b goes to infinity of b to the negative power of k, or b to a negative power. Will be b to the negative k, which is the limit as b goes to infinity of 1 over b to the k, which is 0. If 1 minus p is greater than 0, then you have that this is going to be the limit of just b to the k. For some positive k, which is going to be equal to 0. So this expression is positive infinity if 1 minus p is greater than 0, or if p is less than 1. And it's going to be equal to negative a to the 1 minus p over 1 minus p if p is greater than 1. Now, because if p is greater than 1, 1 minus p is less than 1, this is the same thing as saying that the integral from improper integral from a to the positive infinity of a function f of x, or the specific function 1 over x to the p, this is going to be equal to positive infinity if p is less than or equal to 1, and it's equal to a to the 1 minus p over p minus 1 if p is any value greater than 1. And p here can be any positive real number, any positive real value. But so we figured out all the values of p for which the function 1 over x to the p converges. We're going to see that this is a very important example in terms of applying the comparison tests that we'll talk about later in the lecture. So the next example that we have is the following type of function. It's we'll actually do an applied example using some of those applied formulas that we derived earlier for the volume and surface area of revolution. Now this example is a very interesting example because it's an example of a surface that has initially you might think that the properties of the surface are that we're going to show are contradictory, but there's no contradiction here. It seems like it's contradictory at first, but we'll see that it's actually not. So this next example is sometimes called Gabriel's horn. After the mythical angel Gabriel in the Bible. So we'll take the following function. We'll think about the function y equals 1 over x just keeps getting smaller and smaller and smaller as we get larger and larger and larger with our value of x. And it continues all the way down as you kind of keep getting closer and closer and closer to positive infinity. And we'll consider what's called the surface of revolution, which we've talked about, that's generated by this function. The surface of revolution that's generated when I rotate this function around the x-axis as a cross section of a circle, because it's the surface of revolution. Specifically, it's the surface that looks kind of like a horn, because it's the function 1 over x looks like this from 1 to infinity, and when I revolve that surface around the x-axis, it has this horn shape. It looks kind of like a horn, or like a primitive trumpet from 1 to infinity here. And we could ask a number of different questions, specifically, what's the volume of this surface of revolution? And the volume is going to come directly from our volume of the surface of revolution formula, which will be the integral from 1 to infinity of the cross section. This will be pi times f of x squared dx. But this now is an improper integral from 1 to infinity. We know this is going to be then the limit as b goes to positive infinity of the integral from 1 to b of pi times 1 over x squared dx, which is the same thing as pi times the limit as b goes to infinity of the integral from 1 to b of 1 over x squared dx, which we calculated before. We calculated this in our first example. In our second example, we looked at the integral from negative infinity to negative 1. But if you go through and do this, and I'll kind of do this quickly here, this is also going to be equal to 1. So this will be pi times the limit as b goes to infinity of the antiderivative of this function is negative 1 over x from b to 1. So it's pi times the limit as b goes to infinity of 1 over we'll just, when you plug in here, you get 1 over 1, positive 1 over 1, minus 1 over b. So this limit is equal to pi times 1 minus 0, which is just equal to pi. So this improper integral converges and exactly tells us that the volume that's kind of trapped inside this surface of revolution, inside Gabriel's horn, is equal to pi. Now this is all well and good, and it's showing us something kind of very cool, that we can take our application formulas and directly apply them to improper integrals. But what we will also see is that not all of them are going to converge. Specifically, if we think about the surface area of this surface, call that S. You'll remember from the surface area formula that this is going to be the integral from 1 to infinity of the circumference at any given cross section. That's 2 pi times f of x times the square root of 1 plus f prime of x squared dx. You'll remember that this is the formula we derived for the surface area of any surface of revolution, and it holds more generally if you have the general formula for the circumference of any cross section of the surface. So this is going to be the limit as b goes to infinity of the integral from 1 to b of 2 pi times 1 over x times the square root of 1 plus the derivative of the function f of x. So remember, f of x is 1 over x, so f prime of x is going to be negative 1 over x squared. It's going to be 1 over x squared squared. So this is the same thing as 2 pi times the limit as b goes to infinity of the integral from 1 to b of 1 over x times the square root of 1 plus, and negative 1 over x squared squared is 1 over x to the 4th dx. And you could go through and actually do this antiderivative and get this definite integral. However, I really don't recommend that. And I will just kind of I'll do this down at the bottom. I'll show that. So this, if you go through and do the exact definite integral of this function, the antiderivative of 1 over x times the square root of 1 plus 1 over x to the 4th, you can go through and get the antiderivative of that function. For some functions, it'll be too complicated, but it turns out that for this function right here, you'll end up getting the following. It'll be, the antiderivative of this will be 1/2 times square root of 1 over x to the 4th plus 1 times x squared natural log of the square root of 1 plus x to the 4th plus x squared minus, this is all right here, over the square root of 1 plus x to the 4th minus the square root of 1 plus 1 over x to the 4th. Evaluated from b to 1, and then you'll have to go through, plug in for b and for 1 into the fundamental theorem of calculus, and then go through and get this the value of this limit, the limit as b goes to infinity. Now, doing this is relatively long. This antiderivative calculation ends up being super long, but it turns out that when you take that limit, you're going to end up getting that this goes to positive infinity, which means that this improper integral right here, diverges. This is a good problem to give us some motivation for one of the what's called the comparison test that we'll talk about at the very end of this lecture, which is the following. The idea here is that for any value of x, 1 plus 1 over x to the fourth will always be greater than, strictly greater than 1 for any value of x that you plug in here. So what's called the direct comparison test can be used here to show, without doing this calculation step, without actually doing the antiderivative, that this improper integral has to diverge. So using the fact that 1 plus 1 over x to the fourth is always greater than 1, we can say that this improper integral for the surface area will always be strictly greater than 2 pi times the integral, or the limit as b goes to infinity of the integral from 1 to b of 1 over x, because 1 plus 1 over x to the fourth is always greater than just the constant 1. And this is 2 pi times the improper integral from 1 to infinity of the function 1 over x, which we've already shown is equal to positive infinity. So because of the fact that this improper integral blows up, and this improper integral is always greater than this improper integral, it means that this has to blow up as well. So that the surface area improper integral diverges to positive infinity. And what that means is that Gabriel's horn is an example of a surface that has a finite value for the volume in the surface, but an infinite value for the surface area. So this is a very nice example for a number of different reasons. It shows us that with improper integrals, we can have surfaces that have finite volumes, but infinite surface areas. And this makes sense, a lot of sense, because you can think of like the surface area in some sense as like the total area, the total length along this curve multiplied by the cross-sectional area at every cross-section, just added up, right? And the idea is that the length of this curve is infinite as you go out to the positive infinity along the x-axis. So the fact that it has infinite surface area is not necessarily surprising, but it does have finite volume because there's enough, the function is decreasing fast enough as x gets larger and larger and larger to sort of make the volume integral converge. And so this is an interesting example because it's a surface that has a finite volume but infinite surface area, and it's also a very interesting example because it shows us a very basic application of what's called the direct comparison theorem, or the DCT for short, which we'll write out at the very end of this lecture. So we talked about how there's a second type of improper integrals, the so-called type 2. Right, and we'll define what an improper integral of type 2 is right now. So for an improper integral of type 2, we suppose that function f of x is continuous on some open or half open, half closed interval from C to B. And specifically that f of x has an asymptote at the point C. So the picture here, this is for this picture is going to be for subtype 1. Just like before, we're going to have 3 separate subtypes for type 2. So let's say we're going from C to B for a given function. And that there's some sort of asymptote at C. So maybe the function looks like this, or like this. So this is going to show us for the subtype 1 how to figure out what the improper integral is from C to B. And it's very similar how we're going to define this improper integral, just like the type 1. We're going to say that this improper integral from C to B exists if the limit as C goes to the value, or as A goes to the value C, from the right hand side of the integral from A to B exists. If this limit exists, then we say that the improper integral converges and if this limit does not exist, then we say that the improper integral diverges. And the motivation behind this is exactly the same as before, because we know that if f of x is continuous on the interval from C to B, then for any a value that's larger than C on this interval, the integral from A to B will definitely exist. But if we take this a value in the limit as a approaches C from the right hand side, then we approach the value of the accumulation of this function over this entire interval from C to B. So both of the subtypes, subtype 2 and subtype 1, 2, and 3, are very similar to this subtype 1, and similar to how we defined it before for the general improper integral of type 1. We can go through in an extremely similar manner to how we went through in the first part. So for a subtype 2, this would be, say, integrating a function to the left of the asymptote. An asymptote, say, right here. And the function could be defined from, say, A. So on the open interval, it's continuous. On the half-closed interval from A to the open value of C. And just for argument's sake, let's say that the asymptote is here at C, and the function maybe looks like this. So we say that the improper integral from a to c of this function is the accumulation of the function from a to c. And we can directly define this, very, very similar to before, where if this is, say, some value to the left of c, say b, see that this value, the value of the improper integral from a to c for this function, is going to converge if the following limit exists. It will converge if the limit as b approaches c from the left now of the integral from a to b of f of x dx exists. So if this limit exists, the improper integral from a to c of this function diverges, or converges if the limit exists, and it diverges if the limit does not exist. And just like before, we have a third subtype, which corresponds to the most general type of improper integral of type 2 that we could consider. And this is an improper integral where you have an asymptote, say, at some value c, and you're integrating, say, from some a maybe to some b of a function maybe that looks like this. So it has an asymptote from the left as you approach c, and it also has an asymptote from the right as you approach c. So we want to be able to define the actual improper integral as we approach the asymptote over this entire region from a to b. And we say that this improper integral from a to b of type 2 exists if the improper integral from the left exists, so if the improper integral from a to c exists, and the improper integral from the right exists. So the improper integral from c to b of f of x dx exists. Remember, the improper integral from the left is going to be the limit of this improper integral as this value right here, this value L, say, or L1, approaches c, and the improper integral from the right is going to be the value of this integral right here. The value of the integral from, say, we'll say L2 to b of this function. If both of these values, these limits exist, then the improper integral from a to b is the sum of those two improper integrals. So this gives us a very, 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 very powerful technique for dealing with improper integrals of this type. I recommend doing a couple different examples, but specifically, we can do a similar example to the examples we talked about earlier, and we're going to get a different result, very, very different result to what we got earlier. Let's consider the improper integral from, say, we'll say from 0 to 1 of the function 1 over x to the q, where q is some real number. You could ask for what values of q does the following improper integral converge. And the answer to this question is we're going to get exactly the way that we got it before. Right? This is going to be the same thing as the integral from 0 to 1 of 1 over x to the q dx, which is going to be the only bad point here in this domain is the point 0. So this is going to be, by our definition of the improper integral of type 2, subtype 1, this will be the limit as a goes to 0 from the right of this value. This improper integral is the same thing as this limit. And this is going to have different values for the different values of q. So the limit as a goes to 0 from the positive of the antiderivative of this function is going to be 1 over negative q plus 1 times x to the negative q plus 1 from 1 to a if q is less than 1. It'll be the limit as a goes to 0 from the positive of the natural log of the absolute value of x if q is equal to 1, and it'll be the same as this right here if q is greater than 1, for any value greater than 1. So for this first scenario, when q is less than 1, this is the limit as a goes to 0 from the positive of 1 over 1 minus q times the limit as a goes to 0 from the positive of 1 to the 1 minus q minus a to the 1 minus q, and if q is less than 1, then 1 minus q is going to be positive, which means that this limit right here is the same thing as the limit as a goes to 0 from the positive of a to the positive integer, which is just 0. So this value is just going to be 1 over 1 minus q, which means that this case right here, when q is less than 1, this improper integral converges. And it converges exactly to the function, to the value 1 over 1 minus q. And if you go through and do the same thing for the other two options, when q equals 0 or q is greater than 1, you're going to get that both of them diverge. So this gives us, for improper integrals of type 2, a much different result for functions of the form 1 over x to some power. Right? It means that this diverges if the power of x, q, is greater than or equal to 1, and it converges to 1 over 1 minus q if q is an integer less than 1. So it's in some sense completely opposite to the problem before, right? The idea is that for the other integral we had the opposite case. So for the integral from 0 to 1, say x to the 1 over the square root of x, this is going to converge, but the integral from 0 to 1 of 1 over x cubed is going to diverge, which was the completely opposite scenario to the previous example introduced. So we want to introduce two separate tests right now that kind of utilize this and help us utilize these ideas, because it turns out that two of these results that we've kind of shown can be directly used along with what are called comparison tests. So we saw an example before of what's called the direct comparison test. What we can do is go through and show that we can generalize the direct comparison test and also another test called the limit comparison test. But we'll save that for the next lecture. Thank you very much for listening today. I hope you enjoyed the lecture and learned something, and I hope you have a great day.